Okay, so we've got three different problems today that are all focused on lectures 15 and lectures 16. So that is failure of brittle materials and failure of ductile materials using the absolute maximum shear stress theory. So there's two different failure theories that we apply in this course to ductile materials: the absolute maximum shear stress theory and the maximum distortion energy theory. And when we go over distortion energy theory, we'll talk about what the differences between the two are. But three problems that'll give you a better handle on these. Now you'll see as we go through these problems that applying failure theory is mostly stress transformation and everything that occurred before that. So the incremental amount of learning that takes you from being able to do stress transformation to applying the failure theories is really small. So the majority of the work here is all the stress transformation stuff and what came before that, which is good in terms of getting extra practice with that material. So let me put the first problem up on the board here. So we've got a concrete pad in this problem, and it's a rectangular concrete pad that looks a bit like this and is fairly short. So we'll put some dimensions here. So we've got 3 inches, that's feet, there's inches, 12 inches along the base, and then it's also 12 inches here into sort of the plane of the glass as well. So it's got a square cross section there. And this concrete block is going to be experiencing a vertical applied force that would be sort of distributed over the whole surface, but we're showing as a point load of 250 kilopounds, 250,000 pounds. And there's also going to be a force applied to this top edge that's pointing over in that direction and is an unknown variable F. So I'll read the problem statement here. It says, a 1 foot by 1 foot concrete pad must support a compressive load of 250 kip, which will be applied uniformly over the top surface of the pad. If the concrete has an ultimate tensile strength of 500 megapascals, so we've got sigma U tension equals 500, did I say megapascals? I should have said PSI, 500 PSI. What is the maximum allowable value of the horizontal force F? Okay, so we want, what is the maximum allowable value of F? So I can put that down now for the moment. Okay, so let's think about the problem again. So we're applying a 250 kip compressive load. We want to have, we know that there's going to be a force pushing horizontally over toward the left. And given that the ultimate tensile strength of the concrete is 500 PSI, we want to know what the maximum value of F can be. Okay. All right. So starting off just conceptually, let's talk about what's going on here. Concrete, we know, is a brittle material, so it doesn't have a yield strength. It has an ultimate strength. And the strength in compression is much, much greater than the strength in tension. In fact, if you look at the material property table, you'll see that the ultimate tensile strength listed for concrete is actually 0 in the table. But in this problem, we're going to say it's 500 PSI. Okay, so for all brittle materials, when we apply failure theory, what we're doing is simply comparing the maximum normal stress present in the object to the ultimate strength of the material, and then divided by a safety factor if there's one present. We're not told anything about a safety factor in this problem, so our safety factor would be 1 here. But we're simply comparing ultimate or the largest value of normal stress to the ultimate strength of the material. And of course, the maximum normal stress is coming from Moore's circle for a given stress situation, right? Those would be the principal stresses, and then you'd compare the largest tensile stress to the ultimate tensile stress, and largest compressive stress to the ultimate compressive stress. So let's just do a section cut through the object and look at what's going on in this case. So we'll just do a section cut somewhere through the object, something like that. So let's draw that out. And here's our section cut, like that. And I'm going to put in the hidden lines for the other edges here. Go. Perfect. Okay, so 250 kip acting downwards on the top. Some of the forces in the y direction says that we need an internal normal force that's also equal to 250 kip there. And then we have our load F acting horizontally to the left. So we need to have an internal normal force that's acting over the bottom surface towards the right. That is a force that is parallel to that cross-section surface. So that's an internal shear force, V. Now, V and F exist some distance apart. There's some separation, L, depending on where this actual section cut is taken. So there's going to be a force couple there, creating a moment. So we're also going to need an internal moment here that is M. And the value of M would be the value of F multiplied by L, F times L. Okay. So let's first think about this situation when F is equal to 0. So if F is equal to 0. If F is equal to 0, and we look at a point in that cut cross section. So let's take the centroid of this cross section, right? Maybe it's about right there, and let's set up an axis coordinate system, right? So we've got a y-axis, we'll say, and x-axis coming out this way. Here's our that's our y-axis here, and then we'll have our z-axis coming out that way. And let's take a point right here and call that point point B. So if F were equal to 0, let's look at the stress state at point B. So stress state at B. So we'll draw the volumetric element for the little piece of material at point B here. So there it is. And if F were 0, then our internal shear force would be 0, and our moment would be 0. So all we'd have left would be an internal normal force. So that internal normal force would be creating a compressive normal stress. So let's put that on our element here. The face of our element that's in the section plane is the bottom face there. So we want to put a compressive normal stress on that face. So there's sigma due to N, and that's the counteracting stress there. And let's put our coordinate system over here, x, y, z. So then our in-plane representation for that volumetric element looks like this, where we're drawing it in the xy plane, and we have sigma n that's oriented like that. Okay. If we were to draw Moore's circle for that element there, let's do it right here. So when we draw Moore's circle, we draw positive normal stress acting towards the right and positive shear stress acting downwards. The center of our circle is given by what? The average normal stress, comma 0, because the center of the circle always lies on the horizontal axis. In this case, the average normal stress is the stress in the y direction plus the normal stress in the x direction divided by 2. We have no normal stress in the x direction, so we just have half of sigma n for the average normal stress. And this goes in as a negative because that normal stress is compressive, and we define a positive normal stress as being a tensile normal stress. So the center of the circle is at minus sigma n over 2. Okay, so here we go. So there's the center of, I'll label it actually, there's the center of our circle, and that is at a value of minus sigma n divided by 2. And then the reference location, point A, is given by the stresses present on the right-hand side of our element, right? And there's no stress present on the right-hand side, so we just have 0, 0 there. So here's point A here. And our radius stretches from C to A, and then we have our circle. And I'm just drawing this as a dashed line because we're going to draw another circle that we're actually going to end up using. Okay. So this is the situation if that f is 0. Okay. So of course, when f is 0, the whole cross section, and it doesn't matter which point you choose for point B, every point in the cross section is experiencing compressive stress with no tensile stress at all, because the closest we get to a tensile stress is a compressive stress of 0, right? That side of the circle doesn't actually come onto the tensile side. So let's look now at what happens when we do introduce a force F, right? So if F isn't 0, what do we have? So now, if F is not 0, let's just look at what happens. So if F isn't 0, then we do have an internal shear force acting over the bottom surface there, which means at point B, which I've chosen to actually be along the line of points that experience maximum shear stress from that internal shear force, because we know that, I just sketch that in 2 dimensions there. We have our internal shear force V acting this way. If we were to graph the distribution of shear stress over that surface, right, here's our axis that we're showing distribution of shear stress. Here's the centroid, or the centroidal axis. Then we know shear stress at the edges is 0, and it increases to reach a maximum value at the location of the centroid, right? So that's why I've chosen point B to be there, so that when force F is present, the material located at point B is experiencing the maximum shear force from that internal shear force. So when F is present and when V is present, point B has a shear stress on it. That shear stress is going to point in the direction of the shear force, which is in the positive x direction. So we go over to our volumetric element and add a shear stress on the face that's in the section plane in the positive x direction. And then we can add the other shear stresses that we need to go along with that one there. So this is tau due to our internal shear force V. So this is tau due to V there. Okay. So let's put that on here. So there we have tau due to the internal shear force V. Okay, perfect. So now how does this change the circle now that we've changed the volumetric element, right? So the center of the circle stays the same because we've just added a shear stress, so that doesn't change the average normal stress. The average normal stress is still sigma n plus 0 divided by 2. But point A has changed now. So point A, we've still got 0 for the normal stress on the right-hand side, but the shear stress on the right-hand side is now this value tau V, and because we define positive shear stresses as acting upward on the right-hand side, this is a negative here. So we've got negative tau V here. So point A goes from being located here to being located up here somewhere at a value of minus tau V. So this is point A for our circle now, and I'm just move my label for the center of the circle to the other side there. And now the radius for this circle extends from C to A like this. And you can see what's going to happen now when we draw this circle is that when we sweep that radius R down to the x-axis, we're actually going to have a tensile stress now. So if we continue doing the circle, right, we're going to have something like this, where our first principal stress, sigma 1, is this large compressive stress, it being the first principal stress, sigma 1, because it has the largest absolute value. The second principal stress, sigma 2, that's the largest tensile stress that occurs at point B. So this is why when we add load F, we end up introducing tensile stress at point B, right? Because we take point A and relative to the situation where F is 0, we're moving that upwards and we're expanding the circle while leaving its center location at the same position. Any questions so far about that or what we're doing here following along conceptually? Okay, that's great. All right, so now what we want to do to actually answer the problem, right? Here we're going to be applying this, but with a safety factor of 1 in this case. So we want to be comparing, really out of this equation, we want to be comparing the maximum tensile stress, which is sigma 2, to the ultimate strength in tension of the material, which is our 500 psi. So all that we need to do to answer the problem is we need to figure out what sigma 2 is, right? Okay, so we can do that fairly easily. We'll erase this to give us some more space over here. Okay, so sigma 2 is going to be the center of the circle plus the radius. For the center of the circle, we need to know the value of sigma n, so let's get that first. So sigma n is simply n divided by a, and we've got a normal force of 250 kip, so that's 250 times 10 to the 3 pounds, divided by our cross-sectional area, which it was 12 inches by 12 inches. So we've got 12 times 12 there. Okay, so that is 1.7 KSI. All right, then we look at the fact that to calculate what R is, we also need to know what tau V is. Okay, so tau V, the shear stress due to our internal shear force, is going to be given by our equation VQ over IT here. V is equal to what? V is equal to F. So F goes in here, and that's the variable that we want. Q. Q is, remember, for shear stress, A prime, Y bar prime. So for A prime, we want the area or the portion of the cross-sectional area on one side or the other side of the line that we're calculating shear stress along. So when we're calculating shear stress at B, that shear stress at B is the same as the shear stress that occurs anywhere along a line that is perpendicular to the direction of the internal shear force. And then A prime needs to be one side or the other side of that line. So our A prime, right, is that cross-sectional area there. So that's 12 inches by 6 inches. So we've got 12 inches by 6 inches, and that's our value of A prime. And then Y bar prime is the distance between the centroid of A prime and the centroid of the overall cross section. So that's Y bar prime there. So if this is 6 inches, then that's 3 inches. So we've got a 3 there, and that is Y bar prime. Okay. All right, divided by I, 1/12 base height cubed. The base dimension is always the dimension that is perpendicular to the direction of the shear force. So we're looking at that dimension there. Not that it matters because we've got a square cross section, so they're both 12. But here we've got 12 and another 12 cubed. Okay. And then variable T here is the length of the line that you're calculating shear stress along. So that's another 12 inches there. All right, so that, when you crunch the numbers, comes out to be 0.0104 F, and in units of PSI in this case. Okay. Okay, so now that we have those, now we can go ahead and calculate what the radius is. So the radius of the circle is equal to what? The square root of sigma n divided by 2 squared. So we've got sigma n divided by 2 squared is this value here, 1.7, and let's change it to PSI, so 10 to the 3 divided by 2 squared plus our value of tau V, 0.0104 F squared to the 1/2 there. Now, did I give myself an equation for that? No, I didn't end up simplifying that. But that's okay because we're almost there. So to get sigma 2, we're just taking that value of the radius and adding it back onto the value of C. So let's actually now take the equation that we want to solve and write in everything that we need. So we want to solve sigma 2 is equal to the ultimate tensile strength, right? And we're saying that sigma 2 is our value of C plus R, and we're setting that to the ultimate tensile strength. So let's fill this in. Sigma, or C, is equal to half of the normal stress. So we've got 1.7 times 10 to the 3 divided by 2, and that's a negative value, plus our radius, so this expression here. Okay, let's pop this down here. 1.7 times 10 to the 3. Pretty ugly 3. There we go. 3 divided by 2 squared plus 0.0104 f squared to the 1/2. Okay, and we're setting that equal to 500 psi. Okay. So now we have an equation where the only thing left to solve is F, and that is going to be the maximum F that can be applied before the tensile stress at point B reaches 500 psi. Okay. So doing that calculation gives us F equal to 101.5 KIP. Okay, 101.5 KIP. Now, there's one thing to do here before we go and put a box around this and call it our final answer. So the one thing to recognize here is that because of the presence of this force F, and recognizing that it's quite a large value, there will be an internal moment that's created, right? That is M equals F times L. And what is that internal moment going to do? Well, if we look at the cross-section in just 2 dimensions here, we've got an internal moment that's acting around like this. So it's going to take this side of the cross-section and push it in compression. Moment's acting about the centroidal axis. It's going to take this side, pull it out in tension, and there'll be the linear transition between those two. So over on this far right-hand edge of this concrete pad, there is going to be a tensile stress created from the moment. So sigma subscript m is going to be a tensile stress created from the moment. Now, there's also the internal normal force that we know of course. So there's going to be also a compressive stress at this location, sigma subscript n. But there's a chance that the tensile stress from the bending moment might increase so much that it overcomes the compressive stress and actually ends up being a net tensile stress that's greater than 500 psi before our load of 101.5 kip is reached. Do you following what I'm saying with that in terms of rationale there for why we might end up having a tensile stress at this point that exceeds 500 psi with a smaller force than 101.5 kip? So let's call this point, we've used point B, we use point A in our circle, we use point C. So let's call that point D there. So what we want to do for just a final quick check on this problem, and it doesn't take long, is we want to check that when F equals 101.5 KIP, the maximum tensile stress at point D is below 500 psi. Okay, so that's what we're going to check there. So let's do that quick calculation just to confirm that that's true. Okay, so at point D, our in-plane element is going to look like this, where we have a normal stress due to the moment and a compressive normal stress due to the normal force. And we know what the compressive normal stress due to the normal force is. It's 1.7 KSI, right? So what we're interested in is what is the value of the largest tensile stress due to bending. Now, we said that the moment will be our value of F times L. That moment will be greatest when L is the full 3 inches. So when we're looking at the portion of the concrete pad that is directly contacting the ground, right? So we'll let L equal our 3 inches, which means that this is 3F for our moment, okay? So then the normal stress here, sigma M equals my over I. Our moment is going to be 3 times the value of F, and we said F was 101.5 times 10 to the 3. Our value of Y is the distance from the axis of the moment to the point that we're considering. That's half of the width of the cross section, so we've got 6 inches there, and then I, we've got 1/12 base height. It's supposed to be a 2 base height cubed. Okay. All right. So let's run the calculation there and see what that gives us. What did I get when I did that? I got that the bending stress was 1.1 KSI. Okay, so with the normal stress due to bending being 1.1 KSI, and the compressive normal stress being 1.7 KSI, the net between those is 600 PSI compression, okay? So this is still in compression. About 600 PSI worth of compressive stress there, right? So when F is 101.5 kip, our point D here is still under compression. So indeed, this point B that we were looking at is the first place where the tensile stress of 500 PSI is reached. So now we can put our box around that and put our arrow to it like that. All right, any questions about that one there? Okay, great. Let's do some racing here, and then we'll throw our second one up onto the board. So if that was all okay and you were following along with that, fine. Then you've got a good understanding of how the stress transformation is working, which is great. You reacclimatized to Halifax weather now? yeah. So reacclimatized maybe, but not happy about it. Okay. Yeah. Good. I'm sort of the opposite way, where I'm like, if it's gonna be cold, you know, you might as well have snow that goes along with it, so then you can, you know, do a few outdoorsy things outside. If it was going to just stay cool and be sort of like 12 or 10 degrees all winter, that would be absolutely fine with me. I lived in Auckland, New Zealand for a while, where the temperature really didn't get sort of below like 12 degrees in the winter. It didn't get warmer than 25 degrees really in the summer either, which I thought was perfect. Yeah. Okay, let's check out the next problem here. Okay, so here we have a pipe that is partially sunk into some sandy soil. Drawing that as a very large diameter pipe, that's okay. So here's the surface of that sandy soil there. And we are, let's see, we're applying a torque to the top of the pipe here. So that's torque T. And we're also applying a compressive load that is load F there. And then resisting torque T is a linearly increasing distributed torque. So we've got something that needs to be going in the other direction. So like this. And the torque is increasing as we go downward, like that. I'll draw one more on here. There we go. Reaching a value of T equals 20 L kilonewton meters per meter at the bottom. And this L here is a variable that describes depth, and the whole length of the pipe below the surface of the soil is L equals 5 meters there. And then we've got half a meter of pipe above the ground too, 0.5 meters there. Okay, we've got a cross section, and then also balancing the force on the top, we have a force from the substrate of the soil, F, acting upwards. The pipe's cross section looks like this, where we've got an outer diameter of 200 millimeters, and we have a wall thickness of 30 millimeters. There we go. So let me read the problem statement. A pipe made of ASTM 20 gray cast iron. So ASTM 20 gray cast iron extends to a depth of 5 meters in sandy soil. The pipe was positioned incorrectly when installed. Unfortunate. And it must be rotated by 20 degrees to correct that incorrect positioning. So presumably there's some sort of maybe like a hole in that pipe or a feature, and it should have been pointing in a different direction, but that wasn't realized when the pipe was buried. So it needs to be repositioned by axially rotating the pipe by 20 degrees. Okay, let's get rid of that hole there. All right. Due to pressure in the soil, the frictional resistance to rotation increases with depth in a linear fashion according to the equations shown, right? So if we want to twist this pipe, the ground is going to be twisting back in the other direction, and that resisting torque is going to increase with linear depth because, of course, the deeper we go in the soil, the greater pressure there is pushing in on the pipe. And we know that friction is normal force times coefficient of friction. So as we go down, greater normal force pushing in on the pipe, greater resistance to twisting due to friction on the soil. So hence the linearly increasing distributed torque. In order to rotate the pipe without causing fracture when under applied torque T, so if we did increase T sufficiently to overcome the frictional resistance to rotation of the soil, the pipe would rotate. But of course, applying torque T, which would cause shear stress, by stress transformation would result in a tensile stress too. And gray cast iron being a brittle material, it would be sensitive to tensile stress, but we'll look at the material properties in a second. In order to rotate the pipe without causing fracture when under applied torque T, determine the minimum compressive force that must also be applied. Okay, so the question is, what is the minimum, F minimum, so that we can actually apply torque T, rotate the pipe without causing fracture. So what's the minimum value of F required here? Okay, so let's look at the material properties for gray cast iron for a second. And we're in metric, so I'm going to be looking at the metric side of the material property table. So gray cast iron has an ultimate tensile strength of what, 179 megapascals, and it has an ultimate compressive stress of 669 megapascals. Okay. No yield stress here because cast iron is a brittle material, so it doesn't yield. So we've got two ultimate stresses, one for tension, one for compression. Like most brittle materials, compressive stress significantly greater, compressive strength significantly greater than tensile strength. Okay. So let's go about solving this problem. Okay, so the first thing we're going to do is get a sense of what the loading situation is like within the pipe. So let's do a section cut at this location here where the internal torque is going to be the greatest. Okay, as soon as we start section cutting lower beneath the soil, then we have some of the internal torque here being counterbalanced by some of the distributed torque. So the level of internal torque is going to start dropping as we move below the surface of the soil. So the greatest internal torque in the pipe will be in this 1.5 meter length that's above the ground. So let's do a section cut just somewhere through there. So we've got something then that looks like this, where here's our, then I'll draw the rest of the cross section like that, and it would be nice if that was a bit closer to circular. There we go, that's better. Okay, so we've got our external torque that's being applied, T. Maybe that's not, I was trying not to clutter things up by drawing too many lines close to each other, but I don't like the look of that. So T there, and then we've got our load F. And what are our internal forces going to be? We're going to have an internal normal force that's equal to force F, and we're going to have an internal torque Ti that is equal to torque T. Let's go ahead and figure out what that torque T is so we know what the value of our internal torque is going to be. So we can simply do for this, if we erase the ground here, pretend we're going to erase the ground, then we can do sum of the torques is equal to 0 for the whole object, right? And then we have T is equal to the resultant of that distributed torque there. So in terms of the resultant of that distributed torque, don't let that worry you, because just think about the fact that if you were looking at, so the reason you might be, if you haven't dealt with linearly increasing distributed torques in a while, you might be thinking, okay, I need to calculate the area of something, but this is like a cone-shaped area in 3 dimensions, so how do I calculate that? If you plot the value of the distributed torque little t versus length here, then you've got a linear line where at an L of 5 meters, the value of the distributed torque reaches 20 multiplied by L. Okay, so all that you need to do for calculating the resultant of the distributed torque is take the integral of that line, or take the area of that triangle, right? So the resultant of the distributed torque is just 1/2 base, which is 5, multiplied by height, which is 20. And then we're in kilonewton meters, right? So this torque is going to come out in kilonewton meters, 20 multiplied by 5 again there. Okay. So we've got 25 multiplied by 10, 250 kilonewton meters is going to be the torque T there. So we've got our internal torque then is equal to 250 kilonewton meters. All right. So we're going to do something really similar to the previous problem. Okay. What we're going to look at first to get our sort of heads around this problem is we're just going to look at an element in this object when the applied load, applied compressive force is 0, and consider the stress state there. And then we'll consider what happens when we add our internal torque T into that. So let's pick our point of interest, and I'm going to throw on a coordinate system here for us. So let's make this our x-axis, this our y-axis, and this our z-axis pointing upwards. So we've got right-hand rule, x into y, point z. Okay, for our point of interest, I want to choose the point that is under the greatest amount of shear stress. Shear stress from an internal torque, we know that it's given by the equation tau equals T rho over J. So the shear stress increases with variable rho, which is the distance that the point of interest is away from the center of rotation, or the axis that the torque's acting about. So all points on the circumference here are going to experience maximum shear stress, any point on the circumference. So let's take one of those points. And it always makes sense just to position the point on one of your axes. So I'm going to call this my point B again. Okay, so let's draw the volumetric element for point B. So sort of in the perspective of my, having a terrible time drawing parallel lines here. Man, there we go. Blame it on the cold that I have and my ears being blocked up. I don't know if that's true, but I can blame it on that. Okay. So there's the volumetric element located at point B. In order to get our bearings between these, it's the bottom surface of the element that is in the section plane that we've cut through, right? So those internal forces, the internal torque, the internal normal force, they both act on the bottom plane of that element, so that's where we'll put stresses. So let's go ahead and consider the case if F equals 0. So if the compressive load equals 0, what would the stress state of point B look like? So normal force would be 0 then, and we just have our internal torque. We know what that internal torque would do. It would create shear stress that is in the direction of the internal torque and tangent to the circumference. So that would be pointing in the negative y direction at point B. So our shear stress would be pointing in this direction. There's tau. So on our element, that's a shear stress like that on the bottom surface. And then top surface shear stress like that. There we've got another one, and there we've got another one. Let's put our axes beside. So we said we'd have X, Y, Z there. So here we've got our shear stress, tau. In this case, tau due to our internal torque T. So for our in-plane element, our in-plane element's pretty simple. We're doing this in the ZY plane, right? Looking at the element down the x-axis, so we see all those shear stresses acting around. We've got one shear stress there, one shear stress there, one shear stress there, one shear stress there. So this is tau T. So let's plot more circle now for point B. Okay, so set up our axes for the circle. Got positive normal stress acting to the right, positive shear stress acting downwards like that. Okay, the center of the circle is going to lie at the average normal stress. Let's try that again. Average normal stress, comma, 0, which in this case, the average normal stress, sigma y plus sigma z divided by 2, those are both 0, sigma y and sigma z, so we've got 0, comma 0. So we've got our center of our circle lying directly at the origin there. Point A, our reference point on the circumference of our circle, is given by the stresses on the element's right-hand side. There we go, there's the right-hand side. So we've got no normal stress and a shear stress tau T that is upwards on the right-hand side, so it's positive. So we've got positive tau T. Okay, so down here, here's point A, located at positive tau subscript T, and radius extends from C to A. Then I'm going to do a similar thing. I'm just going to draw this as a dotted line because we're going to discuss how this changes when F is not equal to 0. Okay. So in this situation here, we've got, because there's a torque being applied, we've got a fairly large tensile stress that develops. And because this is the radius, right, this value of tensile stress is going to be the same value as tau T. So I think we've got everything that we need to calculate tau T. So let's go ahead and do that, and we can just see how that tensile stress would compare to 179. So I'm just going to create some space for us to do that over here. I don't think we need any of this anymore. Okay, so tau subscript T is going to be T rho over J, is going to be our internal torque of 250 kilonewton meters, so changing that to Newton meters. Our distance rho, we're at the outer circumference, so the rho, that's the distance from our axis of rotation to the point of interest, so that's the outer radius, which is 100 millimeters, so we've got 0.1 there, divided by J, pi over 2 outer radius to the 4th power minus inner radius to the 4th power. 100 minus 30, 70, 0.07 to the 4. There we go. All right. Let's see what that gives us when we crunch those numbers. So I'll just flip back here where I've got that value worked out already. 209.4 megapascals, 209.4 MPa. Okay. So look at this. 209.4 megapascals is going to be the value of the radius. So the tensile stress there, if the compressive force is 0. The tensile stress is going to be 209.4 megapascals. That exceeds the ultimate tensile strength. So we could not rotate that pipe just by applying a torque without a compressive load, right? The pipe would break before we overcame the frictional resistance to rotation that's being applied by the soil. Okay. So now let's think about how things change when we do apply a compressive load. So now, if F wasn't equal to 0, right? If F does not equal 0, then for point B, we've got now a normal force that's equal to F. So we're going to have a compressive normal stress acting on the surface of the element that's in the section plane. So here we've got sigma subscript n. There's the equal and opposite stress on the top. So now on our in-plane element, we've got normal stress there, a normal stress there, and this one is our sigma subscript n. Okay. What happens now to point C and point A? Well, point A in this case stays exactly the same, right? Because the stress state on the element's right-hand side hasn't changed. But now point C has changed, right? The average normal stress now is negative sigma n divided by 2. Negative sigma n divided by 2, comma 0, right? So the location of the center of the circle moves from here to somewhere over here. So this is minus sigma n divided by 2. Actually, that's a poor spot to put that label because, of course, I'm going to want to show a radius connecting C to A there, and I'll get rid of that one there so we're not too cluttered. Okay, so there's our radius C to A, and this value is minus sigma n. Let's move all the labels around. Minus sigma n divided by 2, and there's point C for the center of our circle. Okay. All right, so since we've kept A at the same location, move the center of our circle over, now when we draw the circle, right, the largest tensile stress present has dropped, right? Has dropped to this value, sigma 2. And I'm calling it sigma 2 again because the larger magnitude principal stress gets labeled sigma 1. So sigma 2 has dropped due to introduction of that compressive load. So the question really is, well, in order to drop sigma 2 to 179 megapascals, because we know with F equals 0, sigma 2 is actually 209 megapascals. So to drop from 209 to 179, what is the minimum value of F that we need to apply to accomplish that? So this is easy to solve, right? Now that we've got all this conceptual work out of the way. Exact same sort of thing as we did last time. Say that, oh, for a brittle material, failure will occur when sigma 2 is equal to the ultimate tensile stress. So we'll set sigma U tension equal to our largest tensile stress, sigma 2. Okay? And then we'll say, what is sigma 2? Sigma 2 is the center of the circle, C, plus the radius, C plus R here. Okay, and then the center of our circle is what? Minus sigma n divided by 2. And then our radius is the square root of sigma n divided by 2 squared plus our value of tau t. Wow, that was a poor attempt at a curly bracket. That's not much better, but we'll go with it. To the 1/2. There we go. So we've got everything that we need now to complete this equation. So let's put some numbers into it and solve. So on this side of the equation, we've got the ultimate tensile strength. So we've got our 179 times 10 to the 6 pascals. Sigma n divided by 2. Sigma n is going to be equal to what? Sigma n here is equal to n divided by a, which is F divided by a. So we've got F divided by a there. So let's put that in. F divided by a. What's a? A is pi over 4, or we've got diameters or radius. Let's just do radius here. Pi r squared, so outer radius squared minus inner radius squared. Outer radius was 100 millimeters squared minus inner radius 70 millimeters squared. Right, so that's the value of normal force. And then we want to divide that by 2. We have our 2 down there, so we'll put our 2 there. And then plus, now the bit in brackets. So I'll just bring that out there. And we've got sigma n divided by 2 again, but squared, so this quantity again. So we've got F over 2 pi and then 0.1 squared minus 0.07 squared, curly bracket, and then another bracket, square that, perfect, plus our value of tau t, which was right here, 209.4 times 10 to the 6, and we want to square that. And then we're raising that whole thing to the power of 1/2 to take its square root, right? So here's our equation, right? Our only variable left there is variable f. That will give us the minimum value of f that we need to apply so that sigma 2 is 179 megapascals. So when I did that calculation, what did I get? 1.1 meganewtons. 1.1 meganewtons, right? This number actually comes out in newtons. I've divided by a million to put it into a better unit here. So 1.1 million newtons. Now, similar to the last problem, before we go ahead and put a box around that and call it our final answer, there's one thing that should occur to you, and that's the fact that 1.1 million newtons is a heck of a lot of compressive force. So if we indeed have to apply that much force to reduce the tensile stress, have we actually exceeded the compressive stress? Compressive stress is a lot bigger than tensile stress, but that's a lot of compressive force, right? So let's just do a double check there to make sure that the compressive stress of the compressive strength of the pipe hasn't been exceeded. So check that with F is equal to 1.1 meganewtons, sigma 1 is less than sigma ultimate compression, right? So check that the largest compressive stress present, sigma 1, is less than the ultimate compressive strength of the material. So that's easy to check, right? Because all we want to do is find the value of sigma 1 here, which is equal to what? The value of C minus R. Okay. So C plus R was right here. So we just do C minus R. So take the same thing here and put it up here, but with F is equal to 1.1. So we've got what? 1.1 times 10 to the 6 divided by 2 pi, and then 0.1 squared minus 0.07 squared plus then this same sigma n divided by 2 there. Create just a little bit more space here. So 1.1 times 10 to the 6 divided by 2 pi 0.1 to the power of 2 minus 0.07 to the power of 2, curly bracket, squared, plus our value of tau t, 209 times 10 to the 6 squared to the 1/2. Okay, equals. What does that come out to be? When I did it, I got 246 megapascals. 246 MPa. Right, 246 megapascals, still well below 669 megapascals, so okay. Therefore, okay, right? So that's okay, so we can actually call this our final answer right there. Okay, questions? Any questions about this one or anything that I did there? Sure. Okay. Yeah. No problem. So we'll do the next problem, and then we can touch on that. All right. So let's look at the final problem here. So now we've done 2 problems involving failure of brittle materials, and the next one's going to be a ductile material. So we'll look at the how to apply the absolute maximum shear stress theory in this next problem. Just clean things up a little bit here. Okay. There we go. Okay, clean surface, ready to make another mess. Let's see what the final problem is. Okay, so this is always fun to draw. Seeing me struggle to draw a helicopter that's not completely laughable. And it's a pretty short rotor, but that's okay. What I mean by laughable, there we go. The tail rotor is almost as big as the main rotor. Okay. A 2,500 pound helicopter. So let's just put its center of gravity right here. 2,500 pounds. 2,500 pound helicopter hovers, neither moving up nor down. The helicopter's motor delivers 245 horsepower to rotor shaft AB. So rotor shaft AB is this guy here, AB. Okay. So being delivered to shaft AB by the motor is a torque and associated with that torque is a power of 245 horsepower. Okay. 245 horsepower delivered to rotor shaft AB by the motor. So that produces torque Tm. Spinning it at 460 RPM. 460 RPM. Okay. Using the absolute maximum shear stress theory, determine the required yield strength of the rotor shaft for a safety factor of 4.5. And there's also a picture here of the cross section of the rotor shaft. So the cross section of shaft AB looks like this. It is going to be a tube because we know that tubes are very good things at resisting torques in a way that doesn't introduce excess weight, because most of the shear stress due to a torque is at the outside. So there's no point in having material where there's not stress. Okay, and the wall thickness here is, outer diameter is 5 inches, wall thickness is 1/4 inch. So the question that we're asked is the yield strength for safety factor of 4.5. Okay, using the absolute maximum shear stress theory. All right, so let's talk about the absolute maximum shear stress theory for a second. So the absolute maximum shear stress theory says that failure of a ductile material will occur when the absolute maximum shear stress in the material reaches a value of the material's yield strength divided by 2 times the safety factor. Okay. So sigma y is what we want. Safety factor we have to solve the problem. The only thing that we need is in that rotor shaft, what is the value of the absolute maximum shear stress? The absolute maximum shear stress comes from Moore's circle. And the way you want to go about finding that for an object is starting by just considering drawing Moore's circle for the point in your object that is under the greatest stress. So let's look at a free body diagram of rotor shaft AB to start with. Okay, so it's a rotor shaft AB. So we've got TM, well, TM should be applied to the bottom of the shaft where the actual motor is. So let's correct that. Could have left that on because we're going to have a counteracting torque, but nonetheless. Okay, so here's our torque Tm being applied by the motor. We have to have, if this shaft's spinning at a constant rate, then some of the torques needs to be 0, so we need to have an equal and opposite torque at the top. Of course, that's coming from the rotor blades. So we've got T equals Tm here. And then we have the weight of the helicopter pulling down on the shaft here. So we've got 2,500 pounds pulling down here. So again, we need to have an upward lift force from the rotors that would be equal to 2,500 at the top here. So if we do an internal section cut at some location, right, then let's look at Excuse me. Let's look at what the internal forces are like. And of course, we've got exactly the same as what I just had on the board, except now this becomes an internal normal force that's equal to 2,500. And the torque is an internal torque, Ti, that's equal to Tm, the torque from the motor there. Okay, so again, let's think about the point that is under maximum stress. So from the internal normal force, that's a tensile internal normal force, so it'll create tensile normal stress. All points in the cross section are going to have that same tensile normal stress from our internal normal force, right? So that doesn't help in determining which point we want to take. We could pick any point that we wanted. The torque, however, we know that shear stress from a torque increases as we move outwards to the circumference of the shaft. So all points on the circumference are going to have the greatest shear stress. So that we want to pick one of those points, one point on the circumference. So let's just set up our coordinate system, and then we'll take a point as our point of interest that's on the circumference. So here's our coordinate system. Let's do X again, Y, and Z like that, and make this our point of interest, point B there. So stress state at B looks like the following. So let's draw our volumetric element at point B. Okay. Good. Axes are always nice. X, Y, Z. The face of the element that's in the section plane is the bottom one. There we go. So, how do the stresses transfer to this element from these internal forces? Tensile normal stress, or tensile normal force, we're going to have a tensile normal stress, sigma, due to internal normal force N right there. Okay, there's the one on the top. And then shear stress from the torque, we're going to want to have it tangent to the circumference in the direction of the internal torque. So here's going to be tau from T, that's in the positive Y direction. And so we just go down to the bottom here and put a shear stress in the positive Y direction on the face of the element that's in the section plane. And our other shear stress is there. So this is tau due to T. Okay, let's calculate values for both of those before we go any further. So for sigma n, that's just n divided by a, which is what, 2,500 pounds divided by a, pi over 4, outer diameter squared, 5 squared, minus inner diameter squared, 5 minus a quarter, quarter on this side, quarter on that side. Internal diameter is 4.5. 4.5 squared. What does that give us when we do it? 670.1 psi. So 670 psi. Okay, now it's time for shear stress tau T. So let's first figure out what the torque from the motor is, Tm. So the relationship between torque and power is power equals T omega. We've got a power of 245 horsepower. 245 horsepower. We need to convert that to pound-feet. So the conversion is 1 horsepower is 550 pound-feet per second. So we've got 550 in here. T, so that means that T in this case, which is Tm, torque from the motor is going to be coming out in pound-feet because now our power is in pound-feet per second. Omega needs to be in radians per second. We've got 460 RPM, 460 revolutions per minute. 1 revolution is 2 pi radians. And converting our minutes into seconds, we want to divide by 60 there. So TM comes out to be 2,797 pound-feet. 2,797 pound-feet. All right, now let's take that up here and figure out what tau T is. Tau T, T rho over J. Our torque, 2,797. Now remember, this is in pound-feet. When you're dealing with stress calculations, you want everything in pound inches PSI. So this wants to be in pound inches now instead of pound-feet, which means multiplying by 12 to change it to pound inches. Rho, the distance our point of interest is away from the axis of the torque. That is going to be the outer radius, half of 5. So 2.5 there. And then divided by J. Pi over 2. Outer radius, 2.5. To the 4th power minus internal radius, 2.5 minus 1/4. 2.25 to the 4th power. There we go. What does that give us? That gave me 3.98 KSI. KSI. Okay. Great. So let's go ahead and draw the in-plane element, and then we'll draw more circle. So the in-plane element, here we go. We're going to look in the ZY plane so that we see all of the stresses there. So that would give us sigma n like that. We've got our shear stress positioned like this. We're in the YZ plane. Okay, and this is tau T. There. Okay, let's set up the axes for Moore's circle. We'll go ahead and draw that. Get rid of the ugly helicopter. Goodbye, helicopter. Okay, Moore's circle. Positive shear stress downwards, positive normal stress to the right, like that. This marker's getting a little bit faint there, so just do a switch up here. Let's see what's it's kind of, that's nice and bright, but almost too bright, almost jarringly bright. It's really orange, but that's okay. All right. So the center of the circle C, located at the average normal stress, comma, 0, right? What's our average normal stress in this case? It is 1/2 of sigma y plus sigma z. Here we've just got half of sigma n. So sigma n is sigma z here. So 1/2 of 670, that's a tensile stress. So it's positive, right? So that is what, 335 psi there. Okay, so let's put the center of the circle on, positive 335 right there. 335. There's the center of the circle. Okay, now point A is located at sigma comma tau for the element's right-hand side. What have we got? The element's right-hand side, there we go. We just have a shear stress T tau, so no normal stress, only a shear stress. The value of T tau is what? 3,980 psi. And that's downwards, so it needs to be a negative 3,980 psi. So we're going up here to 3,980, and this is point A up there. So radius extends from C to A. There's our circle of radius R. So we can sketch this out. There we go. Okay, so when you're thinking about the absolute maximum shear stress theory, I shouldn't have erased that. Abs max equals sigma y divided by 2 times our safety factor. When you're thinking about the absolute maximum shear stress theory, what you want to do is you want to identify your principal stresses, and then the absolute maximum shear stress depends on the signs of the principal stresses. So we've got our first principal stress, sigma 1, is a positive value. Our second principal stress, sigma 2, is a negative value, right? So because sigma 1 and sigma 2 have different signs, so one's positive, one's negative, then the absolute maximum shear stress is the maximum shear stress on the circle, which is the points at the top and the bottom, tau max, which are in turn equal to the value of the radius of the circle. Okay. Now, if sigma 1 and sigma 2 have the same sign, so let's say the whole circle is on the positive side of the axis, or the whole circle is on the negative side of the horizontal axis, then the value of absolute maximum shear stress is the value of the first principal stress divided by 2. Because what happens is that if that's the case, the maximum shear stress on the circle is not actually the maximum shear stress that's present. When you draw your volumetric element from one of the other viewpoints, one of the other in-plane representations, and you draw more circle based on that, you actually end up with a larger circle. For differing principal stresses, it doesn't matter which in-plane element you draw. The in-plane element that we've drawn here will be the largest circle that you get. So this is the absolute maximum shear stress. So knowing this, right, now we can take this equation up here and say that R is going to be equal to sigma y divided by 2 times the safety factor. And then we can think about putting in numbers for this and solving it, right? So we've got R is going to be the square root of that distance and that distance. So we've got the square root of 335 squared plus 3,980 squared equals sigma y divided by 2 times our safety factor, which is 4.5. Sigma y is equal to, what did I do when I did that calculation? 35.9 KSI. 35.9 KSI. No checks required before putting the box around that final answer there. Okay, any questions about that problem there? Okay. Well, then you should be pretty well set up now. If you followed along with this, you're good with this. Then you should be very well set up to do the problems on the problem set for this week. So what I'll do is I will clear a bit of space here, and then we can tackle the question that you have about the project.